Okay, here we are. So we are recording, and let's start with our first chapter, chapter 2. All right, so this is the first chapter, and what we're going to learn about this chapter is we're going to learn about the matter, energy, atoms, and molecules, right? And so I will actually jump to matter and energy. And as we know, the matter is, matter is matter, right? Everything that occupies space and has a mass, right? This includes me, you, the trees, the laptops, everything. And the energy is, on the other hand, is the ability to perform work, okay? And like matter, energy is found in a number of forms, okay? And that's what I'm going to be showing you in the next slides. So in the energy, guys, like whenever we have energy, right, we don't really lose any energy, right? Overall, the universe energy is kind of like constant, right? If you have a kinetic energy, then the kinetic energy is changed to like maybe potential energy, right? But we don't really lose the energy. And heat is, like in this case, is one of the forms of energy, and the light is another. Okay. And then we have these two laws. These are pretty simple definitions. Law of conservation of the mass tells us that if you have a chemical reaction, meaning that if you have A and B, right, producing to C, right? Let's say you have 1 gram of this and then 1 gram of this, right? So the total mass that you can get is going to be 2 grams, right? You're not going to be producing 2.1 grams, right? This is the law of conservation, right? You're going to be always keeping the same basically amount, right? You're not going to be able to produce more. If you do that, then you're going to be like super rich, actually. Okay. And law of conservation of energy tells us that in any chemical or physical process, energy, again, the same thing that I say, we cannot either destroy or create it. It's just simply we are converting from one form to another. Yeah, these are just simple definitions, nothing to worry about it. And I already told you about the energy. You probably like heard about this, right, in high school. The simplest energy that we've learned is the potential energy and the kinetic energy. If you have a ball here, right, if I put the ball here in top of the hill, it has some potential energy, right? But if it's keep rolling, then the potential energy converts into kinetic energy so that it has a speed, right? But at the end of it, whenever it reaches some level, it's going to lose that kinetic energy again, and the speed is going to be zero, basically. But what we are doing is, again, we are changing potential energy to kinetic energy. And so when it comes to matters, we know that there are 3 different matters, right? The solid is solid. If you have like water, again, let's give you the simplest example, water. Water can have 3 different matters, right? It can have a solid, which is ice, right? Then it can have a liquid, right? If you melt the ice, then it's going to become liquid. And then if you actually heat it up, then it's going to become gas, right? And the humidity that we have during the summertime, right, there's a lot of water molecule inside the air, and that's where the gas form of the water. There is this 4th form, you probably didn't hear about it, but it's just, again, kind of like a nice triva, is plasma, right? And what it is now every atoms and molecules, right, if it's stable, it doesn't have any charge, right? Like water, right? The water molecule that we have, I'm drinking water, right? It's not dangerous. And then we have oxygen, for instance, the oxygen that we are breathing. And on air, there's nitrogen too. The large percentage of the air is actually nitrogen, 75% or so. And then we have like argon. These are noble gases that we're going to learn, and some other maybe noble gases, right? So these are, again, molecules, and these are actually, we call them a neutral molecules. Neutral molecule is the molecule that doesn't have any charge, right? It doesn't have a negative charge or plus charge. So this plasma molecule, the plasma matter, sorry, that we are talking about is, again, these are charged atomic particles, meaning that if you have an argon, this is argon gas, and it doesn't have any charge, right? If you somehow, if you are going to be able to manage this argon to give them a charge means like it can have a positive charge or positive charge, or it can have a negative charge, right? So these are going to be called ions, right? So therefore, if you have any gas molecule which is not neutral, then that's going to be your plasma. Again, why? This is actually recently discovered, and there are some intrinsic properties about this plasma. You can play with their properties, and that's why people are interested in learning more about this. But we don't have to worry about it. And so I think in this chapter, the thing that I really want to focus on is, matters is going to have some physical and chemical properties, okay? And whenever the matters is going to react with another matters, right? If you have a reaction of sodium with chlorine, things are going to change. So we want to really learn about the properties of the matters. And so when it comes to properties, we have two of them. One of them is the physical properties, and these are the properties that can be observed and measured without changing the chemical composition of the compound, meaning that it is still the same chemical, right? But the appearance might change, but it is still the physical property. And these properties include state, like whether it's a ice or liquid, right? I mean, if it's a water ice, it's still water, or if it's a liquid ice, so liquid water, right? It's still the water. It can be an ice cube, or it can be a water that you're drinking, but it's still the same molecule, basically, right? The composition of it didn't change. The color, for instance, right? Odor, taste, hardness, and the boiling point and the melting point. These are, again, physical properties, because we know that the water freezes at 0 Celsius, right? And we know that the water actually boils at 100 Celsius. These are, again, physical properties. And I'm going to be actually doing some examples here. So when it comes to chemical properties, after this slide maybe, these are, again, when the chemical composition changes, right? Then we're going to call that's the chemical properties. Okay. So if I want to give you an example, let's do some examples here. Okay, let's do some back and forward. So let's say I have a pencil here. Okay, this is a carbon pencil. Okay, even though I'm using the digital pen, uh, if I break this pen, do you think this will be a chemical change or physical change?
Physical.
Physical change, right? Very good, because again, it's going to be the same pencil, right? The shape of it is going to be just different. It's the same pencil. What happens if let's say I have a paper and I use the shredded paper and I shred the paper. Do you think that's going to be physical change or chemical change?
Physical.
Physical.
Physical, right? Again, it's still the same paper. I just ripped them off, right? The composition is still the same. Okay, very good. What about if I put toast, like now? I'm sure everybody's like hungry now, right? I don't want to make you guys more hungry, but let's say you put a bread on the toaster and then you heat it up. Do you think you're going to have physical change or chemical change whenever you toast the bread?
You're gonna have a chemical change.
Yeah. Again, it's hard to tell, but at least because you're burning the bread right now, right? And whenever you burn the bread, it means that you're applying heat, and then you get like brown stuff, right? This is actually telling you that that's carbon, but that's not the same carbon anymore. Okay. Whenever you break, you burn something, you are actually making more aromatic carbon. Again, I don't want to go too much detail, but that's going to be actually a chemical change. Okay, very good. What about if you have eggs, right? And then you mix the white yolk with the what do you call it? The
Egg white.
Yeah, yeah, egg whites. So if you mix it, do you think it's going to be a physical change or a chemical change?
Physical,
Physical. Why?
because it's still an egg.
Okay, very good. Still the egg, right?
Yeah.
Okay. So this will be my last practice. What happens if you have eggs and if you heat this egg? I mean, you're just heating the egg. You want to have like a nice sunny side egg for breakfast. Do you think that's going to be physical change or chemical change?
Chemical.
Chemical.
Chemical? Why?
The proteins are denatured.
Okay, very good. Why? Because again, whenever you have egg, even though if you have an egg, let me go to my whiteboard. Like for the chemical change, you need to change, right? If you have like C, I don't know, I'm just making up like CXHYOZ, right? This is the chemical formula. You are changing the chemical formula, right? So when it comes to eggs, though, it's a little different because in eggs, this is protein. Again, we are going to learn this in the last chapter. And when you heat this up, you're still having an egg, and the chemical formula or the chemical composition didn't change. It's still protein, right? It's still the protein, same thing. If you have 10 carbon in egg, I'm just making this up, you're gonna have 10 carbons in the cooked egg, right? And if you have like, I don't know, hundreds of hydrogen, you're gonna have the same number of hydrogen, same number of oxygen, same number of, phosphorus or whatever. So why this is a chemical change then? Why it's not physical?
Because you added another element, heat, to change, or you added a type of energy to those molecules.
Okay, but still, I mean, if I add heat to ice, it becomes liquid. I'm adding heat, and that's a physical change. But how come the protein or eggs in this case, whenever I heat it up, it's chemical? You know what I mean? Somebody said something about denaturation. Who was that?
That was me.
Timothy?
Yeah.
Okay, what's denaturation then?
It's a breakdown of proteins from the heat.
Okay, it's not a breakdown actually. Okay, if it will be a breakdown, then there might be, some other interesting. But again, when we're going to learn about proteins, but the proteins are macromolecules, right? These are gigantic molecules. Okay, it's not just a water molecule, and it comes in kind of like a tangle way like that. Okay, and this is called um, um, folding, right? The protein needs to be folded in a specific way in order to act. But these are, again, everything, these are elements, right? Carbon, hydrogen, sulfur, whatever, right? But these are gigantic repeating subunits. And so there are some bonds between them, right? Like hydrogen bonding and other some type of bondings. So when we apply heat, what happens is we are breaking this hydrogen bonding, this interaction, right? And then this is called, as Timothy says, denaturation, and it kind of like loses its folding, right? So it's not folded anymore, as you can see. And so therefore, whenever you unfold it, and some of the process is irreversible, it cannot really go back to here, okay? And especially it's true for the eggs. If it can, then it will be a physical change, right? But for the eggs, obviously, whenever you cooked it, right? You cannot go back to it, and that's why now these proteins is not going to function, even though it has the same chemical composition. Make sense? So
Yeah.
therefore, this is called a chemical change. All right. So
Wait,
yeah,
so
look
it's
at this.
chemical because it can't be switched back to its original form?
True. I mean, not so much, but yeah. I mean, uh, because like if you think about the ice and liquid, right, it can always go back and forth, right? So yeah, I mean, pretty much yeah. If it cannot go back to its original form, then you will suspect that it's going to be a chemical reaction. But again, you need to look also some other things, like you need to look at the composition as well. Okay. All right. Any question? All right, very good, guys. So let's move on. And then in this chapter, we are going to also learn about how to classify the substance, right? Because in chemistry or in science, in any other subject really, right? In order to understand matters, we like to classify them so that we can understand better. And I just want to go over I'm just going to skip this, guys. And I mean, let's give you the definition. And I have the actually slide in a couple slides more. So homogeneous matter is they have the same parts with the same properties throughout. Okay, so let me give you an example of homogeneous matter. Let's say you have. Let me give you an actual example of heterogeneous first. Everybody can see whenever I draw, right?
Right
Yeah.
now, we just see this slide.
Can you
Oh,
see what
no.
I'm drawing here?
Yeah.
Yeah.
Okay. Yeah, sorry. All right, so again, let's say you have oil, okay? And then you have water, right? You mix them up. And let's say I came to the lab and with my pipette, I dip my pipette inside all the way down to here, right?
Mm-hmm.
And I pipette it out just a 1 milliliter of this solution. What do you think this will be? Do you think I will get oil or do you think I will get water?
Oil.
Oil, right? Because oil and water, again, we're going to learn about this in organic chemistry a little more, but they don't like each other, okay?
Mm-hmm.
And when it comes to solution chemistry, like dissolves likes, we're going to learn this about again. And so therefore, it's not going to mix nicely, right? So therefore, if I came and dip it all the way down and take 1 milliliter, this will be pretty much oil, right? And if let's say Timothy came and he was in rush and he didn't really dip his pipette and he was just dipping from the top, right? And then he pipetted out 1 milliliter here. And what do you think the 1 milliliter is going to be mostly like?
Water.
Water, exactly.
Mm-hmm.
So as you can see, right, this is not a homogeneous mixture. This is a heterogeneous mixture. Why is that? Because every time you sampled, right, you are getting a different physical or chemical properties. Okay, so that's why the parts are not unique. Okay, that's what's going to be called heterogeneous mixture. Okay, but yeah.
And when you mix water and oil usually stays on top, right?
Yes.
That's true. Yeah.
Yes.
Yep. My bad. Because again, oil is actually has less dense, right? If you look at the density, yeah,
Mhm.
this is. But let's say something else here. You know, I don't know. Maybe some organic layer like ether, let's say.
Mm-hmm.
Okay. But yeah, it's a good point.
Okay.
Okay. So what about the homogeneous matters? And again, homogeneous matters is if you have a solution, and I'm going to actually explain that to you in a little bit. If you mix, let's say you have your coffee, right? Even though I'm drinking water, and so let's say in your coffee you dissolve like I don't know, like 10 grams of sugar, okay, in coffee, right? And whenever you dissolve something, if it dissolves 100%, then you're going to have a nice distribution, right? You're going to have, again, we're going to learn about the units of the solutions. Let's say you're going to have, I'm just making this up, but 1 molar of sugar in coffee, right? So this means that, right? This means that no matter where you take your solutions out, right? Even here, even down here, you're going to always get 1 molar of sugar. Make sense? And this is going to be homogeneous solution, okay? Or homogeneous matter. So these are, again, how we are going to classify them. And again, if you want to if I want to show you a diagram to kind of like summarize everything up, let me just blow this up so that everybody can see. All right, so if you have a matter, then you're going to have homogeneous and heterogeneous, right? And we already explained what the heterogeneous matter and homogeneous matter. And usually, if it's a heterogeneous matter, right, they're gonna be pretty much mixtures, right? And they're gonna be mixtures. You are not gonna find heterogeneous matter like in a pure form, basically, right? If it's just the water, it's not gonna be heterogeneous. It's gonna be always homogeneous. Make sense?
Mhm.
However, if you look at the homogeneous matter, it can be a mixture, right? And I just give you the example of these mixtures. And if it's a mixture, then it has to be solutions, right? So the solutions, again, let's say you have 10% of sodium chloride solutions, right? Which is salt. Let's say 20% of glucose, which is sugar, right? So these are, again, if as long as the solvent is dissolving everything up, right? If it's dissolved, if the solubility is good, then the solution is going to be always homogeneous mixtures. Okay.
Mhm.
But at the same time, you can have pure substance as homogeneous matters, right? And what are they? It can be a compound and it can be element. These are, again, a little bit tricky, guys. Sometimes students get like confused. So if I want to give you the, let's say, again, I'm drinking water, right? This is my water. And what is the water? It's H2O, right? Right?
Yep.
And so it's H2O. And but in this water, again, it's just a water. Is there any other substance, any other things? I know there are some things, but we're just going to omit like minerals maybe. But we're just assuming everything is water, right? So it's no, right? So everything, I have millions, gazillions of water molecule coming together, and I'm just drinking pure water. So this is going to be my compound. Why is that? Because I have two elements. One of them is hydrogen, and one of them is oxygen, right? So even though I have two things, because they combine, and now it becomes water, okay? But I have only water, and that's why it's going to be a pure substance, and it's going to be a homogeneous matter. Make sense?
Yes.
Okay, good. So let me give you an example then. Do you think, let's go back to our slide. So do you think the breathing air that you are breathing right now, do you think is homogeneous mixture or heterogeneous mixture?
Homogeneous.
Homogeneous.
The air that we are breathing,
Correct. Homogeneous.
why is homogeneous?
Because you have a mixture of elements and compounds that create the air that we breathe.
Okay, do you think, what are we breathing air? What are we breathing in air? Do you think
What's
it's
in
only, huh?
what's in air?
Yeah, what's in air?
You have nitrogen, oxygen.
Good. Like maybe some noble gases, argon,
Yeah.
and some water, right?
Mhm.
Okay. And so do you think you're gonna have a nice mixture, meaning that let's say you are in the ocean, right, next to the ocean. Do you think the concentration of the oxygen is gonna be the same uh, as um, as here?
Yes.
Well, I mean, not only that, but why you are saying this is gonna be homogeneous mixture?
Because air is a compound plus elements and making it a pure substance.
Again, if you look at this, guys, right, you may think that this may be a homogeneous mixture, but I will say this is a heterogeneous mixture, right? Why is that? Because the concentration of the oxygen and nitrogen, first of all, we have 4 different elements, right? And if you look at these 4, maybe 5, or I don't know, like maybe more than that. So if I can come back to here,
Professor, and we also need the carbon dioxide, right?
say it again.
We also need the carbon dioxide.
Oh,
Yes.
carbon dioxide. Yeah, that's true. Yes, we have carbon dioxide as well. So again, in order to have a pure, I mean, if it's in order to have a, I will say actually, let's say, if it's pure, let's say, let's first find out whether it's pure or not. Do you think this is pure? The air that we are breathing,
No.
is it a pure substance?
No, not based on the formula.
No, right? Why is that? Because now we have, again, we have oxygen, nitrogen, argon, right? Water, and carbon dioxide. So it's not pure. Everybody see that, right?
Mixture of an.
Right?
Mhm.
Yes.
Okay, so it's not pure. So if it's not pure, then what is it? Is it a compound? It's not a compound, right? Because now this is a compound by itself.
Mhm.
This is a
Heterogeneous.
compound by itself. This is a compound by itself, but overall, this is a mixture,
Mhm.
right? Okay, everybody see that, right?
Yep.
Okay, good. And then I will say, you know, you may say that it's a homogeneous, but I will say it's a heterogeneous mixture because again, the concentration is going to be slightly different, right? Because if you go to top of the mountain, the oxygen level is going to be obviously different than the ocean, right? If you climb up the hill, the oxygen level is going to go down. And the water, if you look at the water, for instance, right? Sometimes if you are in obviously in a climate like a humid climate, the water level, right, the humidity is going to be high, right? If you are in Texas, humidity is very high, right? But if you are in California, the humidity is low, right? So therefore, again, it's not going to be exactly the same. Okay, so therefore, it's going to be a heterogeneous mixture. Okay, but I think the point that I want to make here is here, right? So this is not, first of all, pure. You should be able to tell me, and it's a mixture. And when it comes to heterogeneous, I will say it's a heterogeneous, but some other professor might say it's a homogeneous mixture. Okay, but based on, again, where are you, right? If you take, let's say, 5 milliliter of air in California, it's gonna have a different composition than 5 milliliter air in China, right? Because they're gonna have more CO2 maybe, right? So therefore, it's gonna be a heterogeneous mixtures. Any question with this, guys? Everybody's fine? Good? All right, very good. So let's move on. And again, we already talked about the elements a little bit here, right? So the elements are a pure substance that cannot be broken down into simpler substance. So that's the simplest substance that you can find on Earth, right? And we cannot really go below elements, okay? So everything else that you see is made out of elements, right? So the thing that we have, it has a carbon, maybe it has oxygen, nitrogen, maybe it has iron, right? Maybe it has aluminum. The smartphones that we are using, it has some, we are going to learn about, like non-metal elements and things like that, right? And so this comes to my next topic. So we can actually classify the elements in 3 types: metals, non-metals, and metalloids, okay? And what are they? I'm going to bring my PowerPoint, sorry. Yeah, this is actually in the next slide. So this is the periodic table, guys, okay? And I know it's not the full scale, but you get the idea. Okay, so this is the periodic table, and you will see that actually in every periodic table, there is actually this, yeah, there are, like, again, some extra elements here that I'm missing. But you see, there's actually this stairways, okay? Somewhere around this region, okay?
Mm-hmm.
Or
And let me
non-metalloid, okay.
use my red color. This is the stairways. Okay. And The periodic table is a very nice instrument for chemists, okay? And everything is very nicely organized. Again, we're going to learn about it in the coming chapter. I don't want to go too much detail in it, but if you look at this, I think we don't have to. I don't have to talk about it. Let me check my notes, guys. Hold on. Maybe it's going to be too much. Hold on, guys. Check my notes. I'm not sure if I have any questions in your quizzes, so let me just double check. This is chapter 2, right? No? Chapter 2. Yeah. Yeah, okay, I have. So, okay, so let's talk about that. All right, so because we're going to talk about the periodic table details, very detailed in the coming chapters. So if you have this, right? Hold on, guys. So if you have a periodic table again, and you can find the periodic table everywhere, right? You can just Google it, or in the classrooms in the MCC, pretty much in the science department, every classroom has periodic table. And I believe there is 117 elements, and still we are counting, right? We are finding new elements, and these are like synthetic elements, by the way. By combining these maybe two different elements together, we are creating an element, but these are synthetic elements, not natural one. Most of them are natural, but some of them are actually synthetic, meaning that you can only find it in the lab, right? You cannot find it in the nature. And so if you look at this periodic table, again, it's a very nicely organized. You can get a lot of information by each element by looking at it, okay? And that's what we're going to learn in this class a little bit too. So here, though, I just want to just talk about this. Whenever we classify the elements, again, we are classifying them in three ways. One of them is metals.
Which is on the middle.
And so the metals are, again, this is my stairways, okay? If everything that's going to be staying on the left of this stairways is going to be metals, okay? So pretty much everything here. There's only one exception, which is this hydrogen here. Hydrogen is, even though it is actually some properties are metals, but mostly it's going to be non-metal because hydrogen is a gas, okay? So these are metals, and everything on the right is going to be non-metals, right? If you have protagonist in the movie, there's going to be anti-protagonist, right? So it's just like that, because these are metals. And what are the metals? They are metals, right? The metals is they are electron rich, okay? And they are like shiny, like this spoon. Not sure if you can see it, but you know, this is, I'm not sure what metal they use, but it's shiny, right? It conducts electricity, right? You can grasp it, you can hold it, and it's hard, and etc. Okay, so these are metals. And the non-metals is going to have all the none, right? So if it's electron rich, this is going to be electron poor, right? If it's solid, this is going to be not solid. You cannot really comprehend, you cannot really get it, because these are mostly gases, right? They are not solid, and they are not shiny, and they don't conduct electricity, okay? And then somewhere in the middle again, these stairways that I talk about it is, these are, you know, we call them metalloids. Metalloids.
Professor, excuse me, what about germanium?
That's what I'm going to talk about right now. Okay, so these are, again, right kind of like in the border, right? So these metals, depending on the temperature T, right, or pressure, if you increase the temperature, if you increase the you know, like if you change the conditions, they can act either non-metal or metals. Make sense? So it can actually, it can be on the both sides. Okay, so that's exactly why people are interested in, because by for instance, if you cool the temperature very, very, very low, right, all of a sudden they act like a metal. Make sense? And maybe if you increase the some other stuff, now they start again. I don't know exactly all the details, but they act like a non-metal, and that's what makes these elements very interesting. And you're gonna see all these elements like germanium, like silicon, all you're gonna see a lot of applications of these elements in our everyday, in our daily life, like smartphones, you know. Like the solar cells that we use, right? They have like different, very, very interesting properties. So meaning that you can play with them, right? But if it's a metal, it's a metal. We cannot really do anything about it, right? If it's iron, it's an iron, right? Even if you heat it up to 10,000 Celsius, it's going to be still iron, but it's going to melt it. It's going to be like a water, right? But these guys, the metalloids, is not going to be like that. It's going to change their properties, and that's why it makes them interesting. Okay, so this is how we classify them. So you should be able to tell me whether if it's a metal or non-metal or metalloids by looking at this periodic table. Okay? Any questions? Good. All right, so moving on, we talk about this. We talk about compounds. And again, atoms are atoms, right? What is the difference between molecule and the atom?
Atom is the smallest particle.
Say it again.
Atom is the smallest.
Yeah. So atom is the ultimate particle that makes up the elements, right?
Mhm.
Like if I say H2O, right? This is a molecule, right? Molecule means that if you have atoms coming together, like I have hydrogen atoms and oxygen atoms coming together and making one water molecule, right? This is a water molecule, okay? And obviously, if you have water, it means that you have millions of gazillions of, if you have like a one glass of water, it means that you have hundreds of millions of H2O molecules coming together, okay? And again, this is an example of molecules, water molecule. And we don't have to worry about this molecular compound. And then you may be actually wondering where the name and the symbol is coming from, right? So most of the time, if you look at the periodic table again, the symbol is coming from actually the Latin name, right? So if you have a copper, the Latin name of copper is cuprum, and then usually with the symbols, in most of the cases, there are some exceptions, but we get the first two letters, okay? So one of them is capital, the second is not, so it's Cu, right? If it's a gold, it's aurum and it's Au. If it's an iron, it's ferrum, it's Fe, lead, etc. Okay, I don't really know the Latin names, to be honest with you guys. Okay, and but you're gonna get familiar with these symbols soon. But I'm not gonna be expecting you to memorize this, guys. Okay, so you can actually use your periodic table whenever you take your exams. Okay. All right, and so this is gonna be the last part of the chapter. And the other important information, guys, and this is a little bit tricky part, but not much. We can actually, again, we are going to learn about this atomic mass, how to calculate atomic mass in the following chapter. But I just want to mention one thing here. We can actually get the molecular mass of a molecule. Okay, so if I come back to here again, I'm going to erase this. Okay, again, let's look at the oxygen molecule and let's look at the water. Okay. Oops. Okay, now you can see it, right? So if I have water molecule, I'm just going to give you the water molecule example. Okay. So in chemistry, whenever we have a reaction, right? Whenever you have A reacting with B, let's say, and then you are getting C, okay? We have this concept called moles, okay? And whenever we do stoichiometry, again, we are not going to go so much details, but you just need to learn about the moles and where it comes from. Whenever A is reacting B, we are getting the C, right? And there is actually, like, it means that there's one here, even though we are not writing it. But maybe I can give you the, hold on, the example of H2O again. Hydrogen coming to oxygen and making water molecule, okay?
Oxygen too.
Oxygen 2, yep. You see it, right?
Yeah.
Okay. So now, as you can see here, again, we are going to learn about this balancing equation and things like that, but you don't have to worry about it now, okay? But this is now, as you can see, this is not balanced. You don't have to worry about balancing again. And so let me just balance this quickly. I can either put 1.5 here, or maybe to make it evenly, let's say this. Okay, I'm just evenly balancing it. Then I'm going to have 2. Okay. Okay. So again, in the we already talk about the conservation of the masses, right? And but in chemistry, there is other thing that we need to be aware is whenever you see this reaction, this means that, right? Because hydrogen, even though on the periodic table it just comes as H, in some, again, we're going to learn about this in the future, it's not going to exist as H in the nature, right? It's going to always exist as H2. Okay, some molecule and some atoms does that. And oxygen is the same thing, right? Oxygen, even though in the periodic table, if you look at it, it's just O by itself, but you will never see O by itself. Whenever we breathe in, we are breathing actually 2 oxygen molecules, okay? I mean, 1 oxygen molecule, but it's 2 of them coming together like that, so that we are breathing in. Anyway, so whenever they make water molecule, 2 of the hydrogen is coming, right? And 1 of the oxygen is molecules coming, and then we are making 2 water molecules. Make sense? That's actually how the chemistry works. And then we say, right? We say that 2 moles of hydrogen molecule is coming together with 1 mole of oxygen in order to produce 2 moles of water molecule. Okay? So therefore, we don't really like say, again, this ratio is just for the moles, right? So it doesn't really mean that when you convert these moles to grams, it doesn't mean that it's going to be 2 grams of hydrogen is reacting with 1 gram of oxygen to make 2 grams of water. This will be wrong, okay? But in reality, though, we cannot really measure the moles, right? There's no instruments to measure the moles. That's the problem. And whenever you go to lab, you can only measure the weight, right? The gram, right? Because now I can say, let's say you have a measure or a balance in your lab or in your kitchen. You can measure 100 grams of water, right? You can put the cap, and then you can actually, measure it, and then you can measure it, right? Make sense? So how I'm going to be converting the grams to moles then, right? And that's going to be a problem. And that's actually where it comes to molecular weight, guys, okay? So how can you find the molecular weight of this water molecule. You can actually do that by coming here to periodic table, and as you can see, there are two numbers on oxygen, right? One of them is on top, one of them is on bottom, okay? And again, we're gonna learn about this in detail, but let's just focus the number on the bottom, okay? So the bottom number represents the molecular weight, okay? Or atomic mass unit. But again, this class is kind of like a baby class. We are not really diving into too much things. But what this means is, okay, what this means is, if you have 1 mole of oxygen, right? And whenever I say 1 mole of oxygen, it means that you have, again, this is going to be, you're not going to be responsible, but this means that you're going to have this many of molecule of oxygen, okay? This is the Avogadro number, by the way. And so this will be actually equal to, again, for oxygen case, we are looking at the oxygen. If you have a 1 mole of oxygen, then it means that you're going to have, this is the atomic weight. Okay, and as you can see, the atomic weight is what is it? 15.999. Again, we're just going to round this up, and this will be 16 grams. Okay. All right, makes sense. So if you measure 16 grams of oxygen somehow, oxygen is a gas, it's going to be difficult to measure, but then it means that you're going to have 1 mole of oxygen. It means that you're going to have this many of oxygen in that 16 gram. Make sense? This is the relationship between mole, grams, and how many atoms. But we don't have to worry about this now. I just want to worry about this, okay?
So, Professor, so you always round up?
Round up.
So
Because-
let's just take phosphorus that's down there. It should be 31 grams.
Yes, but again, it's going to be, if you look at sulfur, what is it? You're not going to, because it's 0, you cannot really round them up, so it's going to be 32.
Okay.
Okay, and yeah, I will usually give you the molecular weight if I need to. Okay, but yeah, we are not going to be going like too much crazy about the numbers, so you can always round it up.
Too late for that.
Yeah,
You already went crazy.
yeah. Okay, so here, so let's go back to again our water molecule. Okay, so this is actually 1 mole of oxygen. Okay, what about 1 mole of hydrogen? Now, if I go back to my hydrogen, which is right here, you see the number?
1.
It's 1.
It's 1, right? So it means that it's actually 1 gram. Okay. And so if I have then, if I combine this and if I make H2O, let's erase this. Now you understand the concept of the mole. So if you have 1 mole of H2O, how many grams is going to be?
18.
18. Again, why? Because now you have 2 hydrogens, and I know that 1 mole of hydrogen is 1 gram, so it's going to be 2 times 1 plus, now you have oxygen, which
16.
is, I know is 16, so it's going to be 18 grams. So if you measure 18 grams of water, right, in the lab, you can do that. You have the balances, right? That's nothing so fancy about it. And then it means that you have 1 mole of water. Okay?
Mhm.
And 1 mole of water molecule, you can say that too. And it means that 6.02 times 10 to the 23rd power, as you can see, 23 zeros. That many of water molecules inside that 18 grams. Okay? Any question with this, guys? So now you get the idea. Let's do some couple practices about this, and you should be able to do like some conversion, right? If I tell you, if you have 1 mole of water, how many grams of water do you have? 18 grams. And you should be able to do this for some other molecule, and you can do same thing for the reverse, right? So let's do some examples. Let me see. Yeah, so let's say if I have, if 1 mole of water is 18 grams, let's say, another questions, you have 5 moles of water. How many grams of water do you have?
90.
How many grams?
90
5
grams.
times 90
90
grams.
90 grams. Everybody get that, right? If you have any questions, guys,
Okay.
please don't hesitate to ask, okay? Now I know that 1 mole of water is 18 grams, right? If it's 1 mole, you can do, again, I know in high school you use like dimensional analysis. You can do dimensional analysis, but I don't think you need to for this. We are not going too much deep again. 1 mole is 18 gram. 5 mole is, obviously you're just going to multiply this, right? 5 times 18 is 90 gram. Make sense?
Yep.
Okay, very good. Okay, so let's do another example, and let's do this time. Let's look at the carbon. Now you can see the carbon. Let's just make sure that everybody's on the same page. Let's say you have 1 mole of CO2. Okay, how many grams do you have?
$44.
44, yep.
Okay, so the carbon is right here, and oxygen is right here.
2.
44.
44.
Mhm.
Everybody agree?
Yep.
Yes.
Okay, so let's do it again. So now I know carbon is 12 here, right? And in my molecule, I have 1 carbon, so it's 12 gram plus oxygen is actually, again, I rounded up this to 16, and I have 2 of them, so that's going to be 2 times 16, right? And if you do the math, it's going to be 32 plus 12, 44 grams per mole, okay?
Mhm.
Very good. All right, let's do one more question and then we can move on. I think everybody's good. So let's do one more. Sorry, I'm not usually using efficiently, I guess, the whiteboard, but so let's do another one. What about oxygen? Let's say you have you are breathing 1 mole of oxygen. How many grams of oxygen you are breathing?
32 grams.
Right? It's going to be 16 times 2, 32 grams. Everybody see that, right?
Mhm.
Okay, good. And so let's do a reverse one. So let's say I ask you to, okay, bring me or measure, let's say. I ask you to bring me 36 gram of water. How many moles of water do you have?
2.
Now I'm asking you to gram to convert this to moles.
2
2
moles.
moles.
1 mole is 18, the other one is 18, 36.
Okay. For this one, guys, I will actually use, again, you can do the same ratio, okay? As we did it, right? We know that 1 mole of water is equal to 18 grams, right? We already calculated. How? Because now I know that hydrogen is 2 times 1 plus 16, right? It's 18 grams. Now I don't have the mole, I don't know the mole, but I know I have 36 grams of water. Make sense? So all I need to do is find here, right? The x is here, right? So this will be 36 divided by 18, right? If this is too hard, I can give you another formula, and again, you can use this formula in pretty much in all the classes. The moles, right? The moles is equal to, number of moles is equal to mass over molar mass. It's the same thing, pretty much the same thing that we did here, but this is the formula that you can use also. Molar mass is, again, like whenever we get the 18, right? If you have 1 mole of that molecule, that's what the molar mass means, okay? So in this case, again, I'm asking how many moles do I have and how many grams of water I'm asking?
36.
36. So the mass is 36 grams, right? Divided by the molar mass is, I know it's 18 grams per mole, right? So if you do the math, it's going to be only 2 moles. Make sense?
Mhm.
If you have any questions, guys, please don't hesitate to ask me.
Hold on.
Is Nuhak is here? Nuhak? Or not Nuhak? So I think Hoydak. What was his name? Hoydak? Hoydak? Maybe I need to check his name. Anyway.
That's moles.
Does this make sense, guys?
Yeah, like mud.
Okay, if you have any questions, please do so. And let's do one more, and I think I'm going to be done with this topic. So again, this is an exercise with the same topic. So let's say, again, let's say you have 128 gram of oxygen molecule. Let's convert this into moles. How many moles of oxygen do you have?
Four.
Right now, 4.
Just oxygen.
Oxygen.
8 moles.
Oxygen is right here. Yes.
Eight.
Okay, so let's do this. Again, you may, even though I say oxygen, right? Look at the molecule here, right? It's not just the oxygen. See that? We have 2 of them. Okay, so you might be actually tempted to use the oxygen's 16 grams as the molecular mass, right? Or the molar mass. But again, I'm talking about O2, right? So you have 2 oxygens. So that's why you need to multiply this 2 by 16, right? In order to find the molar mass of oxygen, which is 32 grams per mole. Make sense? Right, guys? Okay, sometimes, students forget to do that too. Like we forget to, oh, it's oxygen 16, and I'll just plug it in here. No, okay? You need to look at your molecule. And now I know that I can use this formula again. Number of moles is equal to
4.
mass over molar mass. So if I have 128 grams of oxygen divided by the molar mass, which is 32 grams per mole, as you can see, the grams are canceled out, and so you have 4 moles, right? Okay. Does this clear, guys? Crystal clear.
Yes.
Okay, good. Very good. All right, so I can move on, and I think this is the last couple slides. Yeah, these are again same thing that we talk about it, right? So if you have a 1 mole of something, it means that you have 1 mole of that substance, right? If you have 1 mole of pure gold, it means that whatever the molecular mass, molar mass of that gold, okay? That's why, you know, as far as the number goes, right? You're gonna have same number of molecules, right? If you have a 1 mole of silver, it means that you're gonna have 6.02 times 10 to the 23 power of that many of silver. But obviously, the molecular weight is gonna be different because each element has a different weight. Make sense?
Mhm.
Same thing with the lead. If you have a lead pipe, if you have a 1 mole of lead, you see it weighs 207 grams, but silver weighs 107. But even though we have the same number of atoms inside that mole, and if you have a 1 mole of neon, it's a gas, it weighs only 20 grams. But again, you're gonna still have 6.02 times 10 to the negative, not negative 3, sorry, 10 to the 23 many neon, elements like atoms, not elements, atoms. Make sense? All right, guys. So this is, I think, pretty good. And this is actually a nice example. If you have a sugar molecule, like sugar molecule is, let's calculate the sugar. Let's calculate. If you have 1 mole of sugar, which is C6H12O6. This is the formula of glucose. How many grams of sugar do you have? Now it's just a little bit more math, I guess, but pretty much. So you need to go find for the carbons, right? And hydrogens. We know hydrogen is 1, and oxygens, and then you need to multiply that each atomic weight with the number of elements, right?
180 grams.
Okay, somebody's really good at math or using calculator. Right? Carbon is 12. And I know I have 6 of them, so it's going to multiply by 6 times 12 times hydrogen is, I have 12 of them, and I already know, I don't have to go back here, it's 1. And oxygen, I have 6 of them, and I have to multiply by 16. Right? If you do this math, what do you get?
180.
180 gram per mole. So it means that if you measure 180 gram of sugar in analytical balances, it means that you're going to have 1 mole. Okay? But guys, let's, do you want to take a break and then come back? I have 1 more chapter to go, but that chapter is very short, so it's not going to be so long. Or do you want to finish it?
Let's finish it.
Huh?
Finish it.
Yeah, finish.
Yeah, we can
Okay,
finish.
finish it. All right, let's get it over. Huh? All right, so again, this is this second chapter. I mean, like chapter 2. I don't want to go by the chapter name, by the way. I still don't know the chapter's name. But in this chapter, we are going to learn about a little bit about, again, we talk about the matters. Now we are actually going a little bit inside of that matter, right? What's in that matter? Okay. So if you look at the matters, it turns out that actually, right? Again, I'm not going to really go to all the experiments that they've done in the chemistry. You can actually read about it in your book if you want to, or there are a lot of good sources online as well. But it turns out that actually, right, if you have, let's go back to, let's clean this mess up first. Hold on. Let's clean this mess. All right. Now it's nice and clean. Okay. All right. So it turns out that actually, if you have, let's take a look at the simplest examples of hydrogen, right? So it just keep going. Okay, so let's take a look at the hydrogen example. And so if you have like we talk about, right, like if you have 1 gram of hydrogen, what's inside that 1 gram, right? Is there anything else? And we already said that that's the furthest level that you can go down, right? There is no more element than hydrogen. So what is in there, right? And then so we talk about these subatomic particles, right? So they are not a new element, but they are subatomic particles. And what are they? Well, we have, if you look at the hydrogen, for instance, let's take a look at the hydrogen. So we have 1 proton, right? And this is actually the atomic weight, we already said, atomic weight. And then if you look at this number on top, I didn't say previously, but these numbers are representing the atomic number, okay? Atomic number. And what is atomic number is, again, in every element, right? It's going to consist of a nucleus. Forgive my drawing, guys. Okay, so this is the nucleus, and then in nucleus we're going to have protons. Let's say P, and then we're going to have neutrons as well. Okay, and if you look at the charge of the proton is going to be actually always plus, right? And the charge of neutron is going to have no charge, 0, right? And today, we still don't know exactly the purpose of neutron, to be honest with you guys. But I think they are acting like a glue between the protons, because as we know, all the same charges, right? Can you pull together let's say you have 2 magnetic, what do you call that? Let's say you have 2 magnets, right? You cannot really bring the 2 north poles together, right? It's going to repel each other, right? And so it's the same thing, but yet they are exactly positioned in the nucleus, all the plus charges all together, and they don't really explode, right? But there's tremendous of power, tremendous of energy, by the way, inside the nucleus. But whenever we react elements, like whenever the hydrogen, and then it has 1 electron too, right? Hydrogen is 1 proton, and then it has 1 electron. And this is the electron. And again, these are going to be subatomic particles that we have to learn. An electron is going to have, let's put the negative charge on the other side, it's going to have a negative charge. Okay? And when it comes to mass, guys, okay, let's say this is the charge. And then we have a mass. Again, in the slides, I have 1.000 something, but you don't have to really worry about those crazy significant numbers. You can just round it up. The proton is going to have 1 atomic mass unit, okay? And neutron is going to have the same thing, approximately 1. And it turns out that the electron is going to be actually very small. It's going to be 1 over 12,000 times less than proton, 1,200 times, right? If you do the measurements, and so therefore we kind of like neglect this, right? Neglect it because it's very, very less compared to 1. And then we said that it's not going to have any masses at all. It has a 0 mass. Okay, that's what the subatomic particles is going to be. And so if you look at this hydrogen example, where do you think that if the hydrogen, this is hydrogen, right? And then whenever the hydrogen reacts with the oxygen, where do you think the reaction is taking place? What's happening? Like, do you think the reaction is taking place in nucleus or electrons, or what do you think is happening?
Electrons.
Electrons, right? Again, because the nucleus is inside the shell, right? And it's really, you're gonna need a lot of energy to break up this proton. And again, if you change the number of protons, right? This is 4, like the hydrogen is 1, helium is 2, right? You don't want to be like changing the number of protons, because once you change the number of protons, you are changing the element. It's not a hydrogen anymore, right? So therefore, you cannot really play. You cannot play with the number of protons. Make sense?
Yeah.
Guys, give me a minute. I'm just gonna get some water. Okay?
Okay, Tom.
Give me a minute. Okay.
So let me ask you the question.
Good. Mhm.
So what you're saying is elements only attach to electrons that are outside of the shell. You can't penetrate the protons to add to the protons. You can only add. Is that where all elements?
All elements, but I'm just gonna explain to you briefly. Now, I'm just talking about the reactions right now, right? If you have any reactions in chemistry, there's exceptions, and we're going to learn about that in nuclear chemistry as well. But you are not going to be able to, right? Let's say this is another hydrogen, and there's electron here, right? So whenever hydrogens is reacting with itself, they are just actually exchanging the electrons, okay? They are just exchanging the electrons. So if you are going to be combining, if you are going to be hitting these two nucleus together, obviously, see, if you hit them together, then you're going to have 1 proton here, 1 proton here, then you're going to end up with 2 protons, right? Larger nucleus. Look at what happens. See, this is helium, right? And then you're going to be exactly doing that. And then once you do that, this is a nuclear reaction, guys. This is the reaction that's taking place in sun, right? That's the origin of the energy of the sun. There's a tremendous energy, as you can see. Either you split the nucleus or you combine the nucleus. But once you do that, you are creating a new element, okay? And that's not what the chemical reaction is, okay? In the chemical reactions, even though hydrogen is losing its chemical properties, but it's still hydrogen, right? Whenever you have H2 plus O2, you have H2O. It is still hydrogen, right? It's still oxygen, but the chemical property is different, right? Because hydrogen is flammable, right? You cannot really approach the hydrogen with a flame; it will explode. And oxygen, on the other hand, it's an oxidizer. I'm not sure if you have any firefighter here, but they know better, right? You need oxygen for fire. But when they come together, we get water, like we are drinking water. It's the essence of life, right? So that's what the chemical reaction. But still, the hydrogen is hydrogen, oxygen is oxygen, meaning that they have still the same number of protons. But the number of electrons is not the same. That's what I'm trying to explain here. All right, any question with this? Okay, so these are the charges. Again, you don't have to worry about this crazy number. You can just round them up, 1, 0, 1. And again, I already kind of like briefly explained in the periodic table, the number that you see in the bottom is going to be the atomic mass. The number of top is atomic number. What is that atomic number? The number of protons, right? This is the number of protons. Okay. And then we have this term called, again, we cannot really change the number of protons. However, you can, and believe it or not, every element is going to have this properties, right? This is hydrogen, but what happens if you have a hydrogen with the same number of protons, but it has an extra neutrons, one neutron, let's say, and another neutron? See, so this is my hydrogen, regular hydrogen, right? And then you're going to have, see, in this nucleus, you're going to have the same number of electrons, but now what happened? You increase the number of protons, right? And so we know that, by the way, maybe I can tell that to you now. How do you find the atomic mass of an element? Atomic mass or atomic weight, same thing. It's going to be equal to number of protons plus number of neutrons, correct? So now if you look at this hydrogen, this is the regular hydrogen that I have. I have one proton, right? And how many neutron? Actually, in the regular hydrogen, there is no neutron. It's just zero. There is no neutron, right? Because here I have only one. Everybody see that, right? Okay. And so what happens if you have, let's use a red color so that we can see the difference. What happens if you have the same number of protons, right? Because we said that we cannot change the number of protons, but then I'm going to be adding one more neutron by bombarding with a neutron, okay? And now you see that it is 1 plus 1. Now I get a hydrogen with an atomic mass of 2. Everybody see that, right? You see that, right? And this is actually called deuterium, by the way. I don't know how to spell, but we symbolize this by D, okay, deuterium. It's going to be the same thing as hydrogen because the number of proton is the same, okay? But it will have just another weight, okay? The weight is going to be different. And we are going to call this, guys, what we're going to call this? Anybody?
Isotope.
Isotope, right? What are the isotopes then?
Same number of protons, different neutrons, so different weight.
Okay, so the isotopes are, they're going to have same number of protons, but different number of neutrons. Okay? Make sense? Okay, very good. And the one thing with the isotope is, this might be also a little challenging, but I don't think it's going to be that much challenging. You see like how we come and how we show, let me erase this part. You see like we put the bottom atomic weight, right? Atomic mass. And in the periodic table, that's what we do. And on top, we put the atomic number, right? And what was the atomic number again?
Number of protons.
Number of protons. And atomic weight is proton plus neutrons. But in the isotopic notation, we do the opposite, guys, okay? Don't ask me why, but that's what we've been doing. Okay, so whenever we want to tell the isotope, now we kind of like switch around and we put the atomic number on this corner, see, and then put the atomic mass on the other corner. Like we just switch them. Make sense?
Mm-hmm.
Okay. And this is going to be called, again, isotopic notation. The way that we represent, the way that we write is going to be called isotopic notation. Okay. And again, these are examples of isotopes. In regular hydrogen, this hydrogen doesn't have any neutron, right? No neutrons. Zero neutrons. But in deuterium, we have one neutron. So therefore, the atomic mass is 2. Okay. And then we use actually this deuterium in isotopic labeling in nuclear magnetic resonance. Again, we don't have to talk about it. And there is one more isotopes where you can see the hydrogen with 3 mass. Okay, and again, when it comes to all the elements, guys, by the way, let me go back to my, yeah. So for instance, if you look at the carbon here, right? If you look at the carbon, let's take a look at the carbon. Right, what is the mass of carbon?
Well,
12, right? But this doesn't mean that all the carbon is going to have a mass of 12, okay? Again, as I told you, pretty much all the elements, I'm sure there are maybe 1 or 2 exceptions, but almost all the elements is going to have isotopes, meaning that not all the carbon that you have, right? Let's say, what is the carbon? Like sugar, right? Let's say sugar. We just talk about sugar, C6H12O6, right? Let's say you get 10 grams of sugar, right? So if you get 10 grams of sugar, there's not going to be all of the carbons is going to be C12, right? Because I know that there's going to be C13 as well. So in nature, right, the abundance of these isotopes is different, right? And if you look at the carbon 12, you are going to get like 99% almost of all the carbon in Earth. Like if you have like 100 carbon, 99 of them is going to be C12, but there's going to be 1% which is going to be C13, okay? Meaning that it will have 1 more neutrons in it, right? So therefore, the atomic mass is different. So the number that you are getting here is, right, they actually calculated, they multiply this mass with this mass with this, right? And then they add them up and the average number. Make sense? Okay. In general chemistry, when you take general chemistry classes, you know, you deal with those questions. You know, like they ask you find the average atomic mass, but that's what it is. And this is actually a very useful because in real life, right? I can like this C13 is we're going to learn about in nuclear reactions. This is going to be actually a little bit radioactive, okay? And because if the proton nucleus is getting bigger, it's not going to be stable, so it becomes radioactive, meaning that it's going to split, okay? And so therefore, that's how they do the age calculation, for instance, right? If you have a fossil, for instance, they look at the level of C13, and then they kind of like backtrack and they try to find the age of C13. Also in doping, right? If you have an athlete who is actually taking a testosterone, for instance, and if you're taking a synthetic testosterone, the C13 level is going to be different than your body's testosterone, right? Because you are taking synthetic C13, I mean synthetic testosterone, which will have a different level of C13 level. Yeah, again, these are some other topics, but you will see the usage of isotope in real life very effectively. All right, so I think that will be it. Let's do some questions with this, okay? And let's see where we are. I know you guys are getting a little bored here, I guess, but let's do some practice so that we can get some excitement. Okay, I'm just gonna do one more, one example, like a short one with the number of protons and number of electrons, okay? So let's say you have protons here so that everybody's on the same page, okay? Electrons, neutrons, mass number, atomic number, okay. Mass number and atomic mass. Atomic number. Okay. So I'm giving you, I'm just gonna make this up, okay? So you'll just fill in the blanks. Let's do like, I don't know, maybe 2 or 3. Okay, let's say you have, I'm just gonna make this up, yeah, 59 protons. And then you have mass number of 141. And let's say, let's say you have magnesium. And let's say you have 12 here. And let's say you have 13 neutrons. Okay. Again, this is again isotopic notation, right? And then let's do one more here. Just gonna make it simple. Let's say 20 electrons and 21 neutrons. Okay, you're just gonna fill in the blanks, guys. Okay, you're just gonna fill in here, 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 right? And then you're just gonna find here. Okay, let's do this. While you're working on this, I'm just gonna ask you one more question, practice, and then I think that will be it. All right. Did you do it?
Hmm.
Finished? All right, let's do this, the first one together. Yeah, my writing is not so good.
How do you figure out the number of electrons?
Okay, so here, uh, I'm saying you have 20 electrons, right? Okay, and so if you have a 20 electrons, how many protons do you think you're gonna have?
20.
20, right? Again, in neutral atoms, right? And in the periodic table, if the element is not reacted with anything else, if the element doesn't have a charge, it means that number of electrons is going to be always equal to number of protons, right? So therefore, you're going to have 20 protons, right?
Okay.
And so now you have the neutron number, which is 21 here. Can you find the atomic mass?
41.
41.
Right? You can add this plus this, right? So it's going to be 41. And what about the atomic mass? I mean, sorry, atomic number.
20.
20.
Atomic number is the same number of protons, right? Atomic number means the number of protons, same thing. So it's going to be 20 as well. Make sense?
Yep.
Okay, let's do this one. Now, if you have 59 protons, and if it's again a neutral element, and this is a neutral element, how many electrons do you think you're going to have?
59.
59, same, right? Very good. And now this time around, I'm giving you the atomic mass, and you know number of protons, and we know that the atomic mass is equal to, right? Number of neutrons plus number of protons, right?
Mhm.
Okay, we know this. Let me just pull this over a little bit. Right, it is actually atomic mass is, let's just say n plus p. Okay, so if it's 141, this is 141 equal to neutron number is, I don't know, but I have the proton number, which is 59. So what is the neutron number?
80.
82.
82, right? 141 minus 59. And what about the atomic number? Atomic number is again same as the proton number, it's 59. Make sense?
82, not 72.
82? Yes, my bad. Okay. And so let's go with this one. Now I'm giving you the symbol, which is magnesium. And by looking at the isotopic notation, right, you should be able to tell me how many number of protons this guy has, right? It's the opposite of the periodic table. So how many proton?
12.
12.
12, right? This is the number of protons. And now I know the neutrons. And I know if it's a neutral molecule, it's going to have the same number of electrons, which is 12. And atomic mass is going to be, again, proton plus neutron. So it's going to be 13 plus 12, 25. And atomic number is going to be the same as proton, 12. Okay? Any question with this, guys? Everybody's good?
Yes, sir.
Okay, let's do another example. This time around, I'm asking you to identify the correct isotope. Like which one is not the correct, but which one are which of these choices are representing the correct isotope? I think I have four, right? Four options, yeah.
D.
So I have these pairs, right? And I need to find which one is the real isotopes. Some of them are fake isotopes.
C.
Which one?
D.
D. Okay, why not A?
They
Because
have different numbers of protons.
Yeah. So there are different number of protons. Let's pick up red. See, first thing first, the isotope is, what are you going to look at? First, you need to identify the number of protons, right? Same. And number of neutrons are going to be different, right? So as you can see, number of protons is different. So these are even totally different elements. Even though it says X and X, this is not an X for sure. This is something else. Make sense? So therefore, this is not the right answer. And what about this one?
no.
Same reason.
This is actually a little bit tempting because now you may say, oh, look at the atomic mass. They have the same atomic mass, but no, I don't really care about the atomic mass, right? The number of proton needs to be same. So again, this is not the isotopes. These are totally different, again, element. This is not the answer. Let's cross here so that we're not going to have access, too many access. Okay, and whenever I come to C, again, the C is number of protons is still the different, 20 and 21. Okay, so therefore this is cannot be because the proton has to be same. That's our first condition. Okay, and then if you come here, now I have 20 and 20. So I have same number of protons, which satisfies. And if you look at the, again, atomic mass, now see, it's different. What is this telling you? If the atomic mass is different, then N is also different, right?
Mhm.
Because in this one, you have 10 neutrons. Over here, you have 11 neutrons. Make sense?
Mhm.
So therefore, this is the correct choice. And sometimes the other sometimes I see that they look at this one, right? 20, 20, they cross it and they say, okay, this is the right answer. But no, it's okay. Again, you always have to check the number of protons and make sure that they are the same, and then you can go you can look for the number of neutrons. All right. Any questions?
So just a general question for the quizzes, is it primarily just what you're covering here in the lectures, or is it over the whole chapter?
Yeah, it's pretty much what I cover here. You know,
Okay.
again, these are again, attending my lecture is going to be really good for you, because in the book there are sometimes, you know, they go over other you know, stuff even in the same chapter, so we may not be covering everything in the book. And the other thing is, Timothy, you can actually again look for the suggested assignments if you have the book. Okay, you can go over the last part of the chapter, and there is assignment questions like a, you know, like practice questions, and you can look for those questions, which is going to be the one that we cover, and that will also help you.
Thank you.